Since the Greek astronomers' explanation of the celestial spheres did not encompass the phenomenon of retrograde motion, so all the all the laws they made up till that time were ruled out. Interpretation of the data. Ptolemy's idea. The oldest idea was Ptolemy's idea. Ptolemy's description of the universe included unmoving Earth at the center, which is called geocentrism, the Earth being at the center, and Ptolemy attempted to explain retrograde motion using equants, deferents, and epicycles. He used his calculations to make fairly accurate predictions of the positions of the celestial objects. Ptolemy's theory of the universe was one of the longest-lived theories ever devised. His theory stayed for more than 1400 years. Ptolemy's system failed all the requirements of a valid scientific theory based on the observations that were possible at the time. Testable could be used to predict, the Ptolemy system filled all the requirements of valid scientific theories of that time based on the observations possible at that time, and it was testable and it could be used to predict the positions too. As observations continued, the Ptolemaic system failed to reliably and accurately predict exact locations of the observed celestial objects. So initially it seemed everything working very fine with all the available theories, but then it started failing because it could not accurately predict some of the positions of the celestial objects. Then came Copernicus. Copernicus had a different idea for explaining the observations on the motions of the celestial objects, and his idea included the sun at the center, and he named the theory as the heliocentrism, provided the first serious alternative to the Ptolemaic system. He agreed with Ptolemy's ideas about the shapes of the orbits. Both thought the planetary orbits were circular. They differ only one thing, that is, the instead of Earth being at the center, in Copernicus' idea, the sun was at the center. And his ideas were not only well liked by all, especially by theologians. Copernicus' contemporary religious leaders believed that the Earth was the hub of the universe. So he got in trouble because the religious readers believed that Earth is this holy thing, which is the main thing for all these things happen in the universe. And then further improving the observations, even though both Ptolemy and Copernicus could explain most observations, much of what was believed as just a speculation. The major contributions, the Tycho Brahe and then Kepler, to resolve the conflict between the Copernicus and Ptolemaic theories, the Copernicus theories of the universe, astronomers of Middle Ages needed better measurements. And then came Tycho Brahe. Brahe possessed amazing experimental skills. Brahe made impressive measurements using relatively crude instruments, by today's standards, of course. Interesting trivia, in 1566, in a duel with another student, Tycho lost part of his nose. For the rest of his life, he wore a metal insert over the missing part. Brahe lab was the state of the art for late 16th century. Brahe did not have a telescope because it wasn't invented at the time. He made measurements with the naked eye and the series of instruments he invented. Brahe was convinced that the improvement of the astronomy hinged on accurate observations. Tycho Brahe is remembered for his design and use of astronomical instruments. The quadrant, the compiled phenomenon body of data over his lifetime of work in the observatory. Then came Kepler, the world of nature, the world of man, the world of God. All these fit together for Johannes Kepler, who lived from 1571 to 1630. According to Kepler, the sun is at the center of the solar system. So he supported the Copernicus system, which is sun is at the center. Careful observation and the measurement led Kepler to develop the laws of planetary motion. So his laws are still valid. Kepler had proposed 3 laws. The first one is elliptical foci. Each planet moves about the sun in an orbit and that has a shape of elliptical shape, while the sun is at one focus. Equilateral areas. The straight line joining a planet with the sun sweeps out equal areas in equal amounts of time. A planet travels faster when it is closer to the sun. Planetary period. The time taken for the orbit is related to the distance from the sun in a specific way.